Hello, everyone. Today we're going to continue our study of triangles, specifically isosceles and equilateral triangles. By the end of the lesson, you'll be able to understand and apply the theorems related to these special types of triangles and solve various geometric problems. So first up, we have to know what isosceles and equilateral triangles are. So an isosceles triangle is a triangle with at least two sides of equal length. And it has a couple different components that we're going to label here. The legs are the two congruent sides of the isosceles triangle. So that would be this one and that one. The base is the side that is not congruent to the legs. That would be that side over there. The vertex angle is the angle that is opposite to the base. Opposite means across from. So we're looking at this angle over here. So that is our vertex angle. And the base angles are the two angles that are adjacent to the base. Which would be that one right there and that one right there. So as you can see, the isosceles triangle has a couple different components, and we have special names for each component of that triangle. Equilateral triangles are a little simpler. An equilateral triangle is a triangle with all three sides of equal length. So all three sides of the triangle have exactly the same length. Another feature of equilateral triangles is that all of the angles are exactly the same measure. So an equilateral triangle is also equiangular. All angles are equal and they all measure 60 degrees. So we have a couple of theorems relating to isosceles triangles. The first theorem related to isosceles triangles is called the base angles theorem. If two sides of a triangle are congruent, then the angles opposite those sides are also congruent. So at the end of the day, what that means is that the base angles of isosceles triangles are always congruent. If two sides of a triangle are congruent, then it is isosceles. And the base angles of isosceles triangles are always congruent. So in that case, these two angles, the base angles of this triangle, are congruent because we have two congruent sides. Now that theorem also has a converse. The converse says that if two angles of a triangle are congruent, then the sides opposite those angles are also congruent. Basically, a triangle with two congruent angles has to be isosceles. So if two angles of a triangle are congruent, then that makes them the base angles of an isosceles triangle, meaning these two sides, the sides that are opposite those congruent angles, have to be congruent. There's also a couple of corollaries to the base angle theorem. Corollary number 1 says that an equilateral triangle is also equiangular, and the converse of that corollary is an equiangular triangle is also equilateral. And that follows pretty clearly from the definitions of those theorems. An equilateral triangle would have all three sides be the same length. And if all three sides are the same length and all of the angles across from those sides are also the same measure, then all of the angles and all of the sides have to be the same. Now, a couple properties of equilateral triangles in particular. Again, all of the sides of equilateral triangles are congruent, and all of the angles are congruent. And equilateral triangles you can think of as just a special case of isosceles triangles. And one thing to note about the angle measures, since the sum of the interior angles in any triangle is 180 degrees, that means our three interior angles, since they're all the same, have to add up to 180. So we have 3 times the angle equals 180. That means that each of the interior angles of an equilateral triangle has to be 60 degrees. So we have a couple of problem-solving strategies that we can use when we're working with equilateral and isosceles triangles. Our first strategy is to identify congruent pairs. We want to look for information about equal sides or angles and use our base angles theorem and converse to find unknown measures. A lot of times they'll give you one piece of information, but that one piece of information can help you find 2 or 3 other pieces of information that will let you solve the problem. Strategy number 2, sometimes we have to use algebra. Sometimes we will have to set up and solve equations based on congruent sides or angles. If you know 2 things are congruent to each other, but you don't know specifically their measure, but you have an expression that represents that measure, you can usually set up an equation between 2 congruent elements and use algebra to solve for the missing variables. And number 3, we want to apply corollaries. We want to recognize when a triangle is equilateral. And that usually simplifies our calculations quite a bit, because as soon as we know that a triangle is equilateral, we know the interior angles are 60 degrees, and we know all of its side lengths are equal. So we have a couple of examples here. In example number 1, we have a triangle ABC, and in triangle ABC, side AB is congruent to side AC. And they tell us if the measure of angle B is 70 degrees, they want us to find the measure of angle A and the measure of angle C. And we've drawn this over here. We have a triangle ABC with 2 congruent sides, AC and AB, with the measure of angle B equaling 70 degrees. Your problem may not always give you a visual, so one skill you guys should learn is to build a visual diagram based off of a verbal description like the one in the problem statement here. But the problem wants us to find measure of angle A and measure of angle C. Since side AB is congruent to side AC, that means triangle ABC is an isosceles triangle with AB and BC, or AB and AC rather, as the legs. We know, based on our base angles theorem, that angles opposite the legs of isosceles triangles are congruent. What that tells us is that angle B, which is opposite to side AC, is congruent to angle C, which is opposite side AB. And since those 2 angles are congruent and we know B is 70 degrees, then we know the measure of angle A also has to be 70 degrees. We also know that all of the interior angles of a triangle have to add up to be 180 degrees. And since we know 2 of those 3 angles are 70 degrees, we can solve for the measure of angle A, which of course has to be 40 degrees when we add up 70 and 70 and subtract that from 180. So the measure of angle A then is 40 degrees. In this second example, we have triangle XYZ, which we're told has angles measuring 50 degrees, 80 degrees, and 50 degrees. The question asks us, is the triangle isosceles? And again, I've given you guys a diagram over here to inspect this triangle visually. Sometimes you will get a visual diagram, sometimes you will not. If you don't, I would highly encourage everyone to draw one. So, by the converse of the base angles theorem, the sides opposite the two 50-degree angles are congruent. Basically, we have two congruent angles as the interior angles of a triangle. And the converse to the base angles theorem says that if a triangle has two congruent angles, then that triangle has to be isosceles. And the sides across from those angles have to be congruent to each other. That means that side xy has to be congruent to side yz. Therefore, that means that triangle XYZ is isosceles. It has at least two congruent sides. In our third example here, our problem states that we have an equilateral triangle which has a perimeter of 18 units, and it wants us to find the length of each side. Now, this is a fairly simplistic diagram because we don't even know the names of the vertices of this triangle. All we know is that it has a perimeter of 18 units and that it is equilateral. But since equilateral triangles all have the same length sides, we know that, for example, all of these sides can be represented by a variable, s. And we know that the perimeter would have to be, well, adding them all together, you would get 3 times s. But we're already given an expression for the perimeter. We know the perimeter is 18 units. So we know that 18 has to be equal to 3 times the length of one of the sides of this equilateral triangle. And when we divide 18 by 3, we get the side length as 6 units. What that means is that this equilateral triangle has side lengths that are all 6 units. Now we're going to move on to a couple of practice problems. In practice problem number 1, we have a triangle, DEF, and it tells us that in triangle DEF, side DE is congruent to side DF, and the measure of angle E is 65 degrees. It wants us to find the measure of angle D and the measure of angle F. Go ahead and try this on your own, and we'll go over the answer in just a second. Ready? Okay. So, since we know that this is an isosceles triangle, we know the base angles are congruent. So that means angle F is congruent to angle E, which means they are both 65 degrees. And then we know that since the interior angles of a triangle add up to 180 degrees, that means the measure of angle D plus the measure of angle E plus the measure of angle F equals 180 degrees. Well, we know 2 of those measurements, so we know that the measure of angle D plus 65 degrees plus 65 degrees equals 180 degrees, which means that the measure of angle D plus 130 degrees is equal to 180 degrees, meaning that the measure of angle D must be 50 degrees. And since we already said that the measure of angle F is also 65 degrees, we have finished the problem. Because our problem only asks us to find the measure of angle D and the measure of angle F, and we have completed that task. In practice problem number 2 here, we have triangle GHI, which has side lengths GH equals 7 centimeters, HI equals 7 centimeters, and IG equals 5 centimeters. The question asks us, is triangle GHI isosceles, and to justify our answers. Go ahead and give this one a shot real quick, and we'll go over the answer in just a second. Ready? Okay. As you can see, I've drawn a diagram for you to the right here. And we have a triangle with 2 equal side lengths. So by the definition of isosceles triangle, which again is a triangle that has at least 2 congruent sides, since side HG is congruent to side HI, triangle GHI is isosceles. It has at least 2 congruent sides, and by that definition of isosceles triangle, that means that triangle GHI is isosceles. And you could take this one step further to justify your answers. You could justify that side HG is congruent to side HI because they have equal lengths. But going that deep into the nitty-gritty is not something I expect you guys to do. It's fairly obvious from the problem that this triangle is congruent, but we base our justification off the definition of an isosceles triangle. In this third practice problem, the problem tells us that if an equilateral triangle has a height of square root of 3, find each side length. Hint, use the Pythagorean theorem. And I have gone ahead and drawn a diagram for you at the right here, since this is one of the more involved practice problems that you might be confronted with. Go ahead and give it a shot. Remember, the Pythagorean theorem can only be used on right triangles. So you might not necessarily use it on the equilateral triangle, but on one of its component triangles that it was split into. Go ahead and give it a shot, and we'll go from there. Ready? Okay. We have this right triangle that was created by the height of the equilateral triangle intersecting with one of its sides. And the height of an equilateral triangle has to split the opposite side into 2 parts if it is an equilateral triangle. So what we have here is a right triangle, and we don't know anything about the outside sides of this triangle yet, but we can give ourselves an expression on what those side lengths could represent. We have an expression here, x, that represents the length of half of one of the sides. And so if x is half of one of the sides, then 2x has to be a whole one of the sides of the equilateral triangle. And we can go ahead and use this triangle, put it into the Pythagorean theorem, and use that to solve for the value of x. So we have 2 legs and a hypotenuse. A squared plus b squared equals c squared. Let's make our a equal to x make our b equal to square root of 3. That means our c is equal to 2x. So we have a squared, which is x squared, b, which is square root of 3, so x squared plus square root of 3 squared equals our value c squared, which is 2x squared. Keep in mind our rules for simplifying exponents. Square roots and squares cancel each other out, so we have x squared plus square root of 3 equals, and here the 2 and the x both get squared, so 2 squared is 4, and x squared is, well, x squared. We can subtract x squared from both sides of the equation. I'm going to go ahead and flip the sides of the equation here to get 3x squared equals 3. And I realized I've made a mistake in our previous step here. The square root of 3 squared is just 3. 3x squared equals 3. If we divide both sides by 3, that gives us that x squared equals 1. And there are only two values that when you square them, you get 1. So that means x has to equal 1 or x has to equal negative 1. This is where the context of our situation is very important. We're talking about the side lengths of a triangle. And the side lengths of a triangle can never be negative. So finally, we have x equals 1. But our problem asks us to find the length of each side. Have we done that? No, not quite. X represents half of one of the side lengths. The entire side length would be c equals 2x. Or, in our case, we can substitute s for the side length. S equals 2 times x. And if x is equal to 1, then our side length is 2 units. And we have then successfully solved the problem. So today we have explored the properties and theorems related to isosceles and equilateral triangles. Understanding these concepts is crucial for solving geometric problems involving these shapes. Remember to look for equal sides and angles, as they are vital clues for your problem-solving processes. Keep practicing, and you'll become proficient in identifying and utilizing the properties of isosceles and equilateral triangles to solve complex problems. See you next time.